Hello friends, welcome back to the videos lectures on fluid mechanics. In the previous section, we have studied about the hydrostatic forces on various plane surfaces or in curved surfaces which are submerged in a fluid. So now moving on, in this section, we will study about the buoyancy and flotation. So we know that whenever from the experience, we can say that when we go to for a swimming, we feel some condition of weightlessness. So this is due to the force of buoyancy which is acting by the fluid on our body. So here it is nothing, it is a body. Whenever a body is submerged in a fluid, say it is an upward force acting on a body on a fully or partially submerged, it should be written submerged body in a fluid. When a body is fully or partially submerged, a force which is acting by the fluid on that body is known as the buoyancy force. So by taking an example, say it is a weighing machine having a mass, say 7, it is showing a 7 Newton weight. It is showing a 7 Newton weight, and a tank is containing liquid. When we allow this body to submerge in the liquid, some water will be spills out because the volume of this body has displaced some volume of the water. So that much volume of the water is displaced, spills out from the tank. So that much amount of volume displaced by this body, that much amount of the volume displaced of this body, that much amount of volume of liquid is coming out from this tank. So let's say a 3 Newton, the water coming out from the tank, say of weight 3 Newton weight is coming out from the tank. So that much amount, the water is coming out from the tank, that force will be acting by the fluid in the upward direction at the body. So 3 Newton force will be acting upward direction in the body. So the force will become, it was earlier have 7 Newton which is acting downward, 7 Newton. Now it is showing 4 Newton which is 7 minus 3, 4 Newton. So this is the condition of weightlessness. So due to the and this buoyancy force arises due to the difference in the density of body and the fluid. So it is this is the Archimedes principle. What is it say? What is it states? When a body is submerged in a fluid, an upward force is exerted on a body, which is a body submerged in a fluid. An upward force is acting on a body which is equal to the weight of the fluid displaced. Say we have seen here the weight of the fluid which is displaced, that much amount of force is acting upward to the body. So this is known as the Archimedes principle. So now moving on, the center of buoyancy is the point, on a body where the resultant buoyancy force is acting. So suppose a tank is there, a body is submerged. We are talking about a submerged body. The volume is displaced by this body, say it has a volume V, so same amount of volume is displaced by this body, same amount of volume of fluid displaced by this body. So the volume displaced by this body, say water, say this liquid is having a specific weight omega. So if we multiply the omega into volume, what will we have? Omega is nothing, rho g into volume. So rho into V into g. So it is nothing, it is the mass. It is the mass of the fluid displaced, because we are talking the volume. So it is the mass of the fluid displaced. So it will become Newton. This much amount of weight of fluid has been displaced as we have submerged that body. So this much amount of force will be acting in upward direction, and that force will be passed at a point of the centroid of the displaced volume. Okay, it will act at the centroid of the displaced volume. So that point is known as the center of buoyancy. So moving on, it coincides with the center of the displaced volume. Okay, if a body is fully submerged, in that case it coincides with the center of gravity of the body. But here the body is fully submerged, the center of gravity of this body will coincide with the center of buoyancy, but it will coincide only in one case, when the mass of this body is uniformly distributed all over its volume. Okay, then the center of gravity of this body will be at the center of this body, of this volume, and in that case the center of buoyancy will be coincide at the center of gravity. So here the center, now just talk about the condition when the body is fully submerged. I talked about it earlier already. The weight which is acting upward is rho v into g. Here this is the weight, say it is the v displaced by this body. This is the v volume displaced, volume of fluid displaced. So this is the volume of fluid displaced, which is equal to the volume of body because it is submerged. So that much amount volume into the specific weight. This specific weight is of fluid in which the body is submerged. So this is the force which is acting upward. Okay, this is the force which is acting upward, and this body since this body have the uniformly distributed mass all over the body, all over the volume, so the center of gravity of this body will lie at the centroid of this body, and centroid of this body is centroid of this body is the point where the center of buoyancy is acting. So there's three things: center of gravity, centroid, and center of buoyancy. When the mass is uniformly distributed, the center of gravity will be equal to the centroid of this volume, and center of buoyancy will always act at the center of the displaced volume. So in that case v will be equal to g. Okay, understand? Now moving on. So the second case is when the body is completely submerged and it will lie on the interface of two liquids. So here liquid of specific weight omega 1 and specific omega 2, the body is lying at the interface. So some volume of this due to this body, some volume of the liquid having specific weight omega 1 is displaced, and some volume of the liquid having omega 2 specific weight is displaced here in this portion. So the buoyancy force acting by this fluid will be in the upward direction, and by this fluid will be in the upward direction. So we can write, let's say it is the FB1 and it is the FB2. So it is nothing. Buoyancy force acting by the top fluid on the body, which is omega 1 having the specific weight into volume displaced. Volume displaced is nothing. It is the volume displaced by the body in the in that part of the body where it comes in the the volume displaced by this body, the volume of fluid displaced by this body will be that portion. That portion is the volume displaced, and it is nothing, it is V1, and volume displaced by the lower body, volume displaced by the lower portion of the body will be V2. So we can write FB1 is nothing, it is the omega 1 V1, that is volume displaced, omega 2 V2, volume displaced by the lower portion of the body. So this is the total buoyancy force which is acting upward on the body. So now this is another case. Say it is now floating on a body, it is not fully submerged, it is floating on a body, the fluid having specific weight again omega 2, and it is surrounded by air. Say air having specific weight omega 1. Obviously air is a fluid, it is also having a specific weight. So whenever a body is floating, we can consider a body is in interface between it is lying at interface between a liquid and air. So here having a specific weight omega 1, but we know that omega 1 is very much less than the omega 2. Specific weight of air is very much less than the specific weight of liquid. So we can neglect this term. So what will we have? Fb will be omega 2 V2. So directly we can calculate, when a body is in floating condition, the amount of volume displaced by the body of this liquid. Say this is a V2. So V2 into specific weight of the water, omega 2. So this is the amount of buoyancy force which is acting in upward direction. So this is how we calculate the buoyancy force. So now moving on. Now we are talking about the condition when the body is in floating, which is not in body is not in submerged condition. It is now floating at the interface. So it is the it is a body having some unit thickness. Say it is a cross section of this body which we are showing in the diagram. Say at this point G is acting here. G is acting in this portion, okay, acting downward. And the volume displaced by this body here, the volume displaced by this body, the center of buoyancy will be acting at the center of this displaced volume here. It is given here. So the G, center of gravity, weight of the body lying downward at the center of gravity, and buoyancy force will be act upward at the center of buoyancy. Now if we give a little angular displacement, a little angular disturbance to this body, how the condition will change. Now in this case we have given a small angular tilt. So the shape of this displaced volume is now changing. The shape of this displaced volume changes means the centroid is all as well will change, which was first earlier lie here in that diagram. It will now become here. So the displaced volume changes, the center of buoyancy will become here. The center of this volume become at B, and we know that center of buoyancy force will act at the center of buoyancy. So now, so just extend this line, this center of buoyancy, in vertical direction. It will cut at a point M. It will cut at a point M, and this at a point M at the line, at the vertical line of this at the vertical axis of the body. So this M will known as the metacenter, and here already G is acting downward and M is acting, the force is acting in the upward direction. So if we talk about this condition, it will be more clearly, okay, M, G, here G, so M at G, the weight is acting downward, W, and here M, the buoyancy force is acting upward, FB. So a couple is generated here. A couple is generated. Due to this couple, it will tends to body to move in counterclockwise direction. Okay, so it will tries to moves body in a counterclockwise direction. So we'll talk about the stability condition in the later slides. So this is the metacentric height, where the center of buoyancy cuts the vertical axis of the body. So a floating, so what is the metacenter? A floating body is given whenever angular displacement, the body is start to oscillate at a point, about a point. So this point is M. So whenever body given a small displacement, it will about to oscillate about metacenter. It will oscillate about metacenter. So metacentric height is nothing, it is distance between the metacenter and center of gravity. Okay, so and from this case we can easily we can tell one more thing. As the metacentric height is more, the restoring couple will be higher. As this metacentric height will be more, the restoring couple will be higher, and body will tends to move in the original condition as soon as it possible. Okay. So now moving on the stability condition for submerged body. When a body is submerged in a fluid, say it is a body given having some non-uniform mass distribution, the mass of this body will be at the lower, more mass of this body will be at the lower position. So the center of gravity will be at the a little bit close to that mass, which was if this body is uniformly the mass is uniformly distributed, it will lie, the center of gravity will lie at the center of this body. But now as the mass is more concentrated at a point at a lower portion, the center of gravity is shifted a little bit lower. Here a buoyancy force will be act at the center of this body, because it is the volume, it will act at the displaced volume. So it is the displaced volume will be of this liquid, and the centroid of this displaced volume is the point where the buoyancy force is acting. So here the center of gravity will be acting downward and center of buoyancy will be acting upward. If we give a little displacement, a little angular distortion, a couple will be act, and this couple is the restoring couple. This is the restoring couple, because this couple will trying to move the body in the original condition. So this condition is known as the stable condition, when the gravity center of gravity lies below the center of buoyancy. Okay, and if the center of gravity lies above the center of buoyancy, it condition is known as equilibrium condition. Here the center of buoyancy is lie below the center of gravity. If we give a little angular displacement, so this couple will try to move the body in clockwise direction, and this is the overturning couple. And because due to this couple, the body will keep on turn in the clockwise direction, it will not come to the original position. So this is the unstable equilibrium, and equilibrium is when the G is coincide with the B. So when the center of gravity coincide at the center of buoyancy. So there is one more thing, when the body is submerged, the concept of metacenter does not arise, because the body is submerged in the fluid. When we give some angular displacement, so the volume of the displaced body doesn't change. Sorry, volume of the displaced mass of fluid does not change, as in case of the floating body, because here when we give a little displacement, the shape and the volume is displaced. The shape and the volume of the displaced fluid changes, and that's the reason where the metacenter point is arises. But here there is no point. There is no point like metacenter rise in the submerged body, because the shape of the body doesn't change in submerged condition. Now talking about the floating body, stable equilibrium is when metacenter lies above the center of gravity. Here we talked earlier, it is the restoring couple which is acting in this direction, but and in this case the metacenter will be at above the center of gravity. Metacenter will be at the above the center of here. Metacenter will be at above the center of gravity. It is the B which is acting here. So metacenter will be of the. So this is the condition of stable equilibrium, and for unstable equilibrium, M will lie below the center of gravity. Okay, and for neutral equilibrium, metacenter will coincide at the center of gravity. So this is the question directly asked in the examination. What is the condition for stability of submerged body, and what is the condition of stability of the floating body? So just keep important notes of this slide. Direct question comes in the examination from this portion. So metacentric height, if we talk about the metacentric height, we have already talk about the metacentric height. It is the distance between the metacentric point. It is a distance between the metacenter and the center of gravity. So it is a distance between the metacenter and center of, sorry, this is the center of gravity, this is the metacenter, So it is distance between center, meta center and center of gravity. So we can find by this formula, it is the moment of inertia of a body when we see a body from the top surface. Let's say when make a top plane. Okay, when we make a, so this is the top view. Say L is the length, B is the breadth. It has the longitudinal axis and a transverse axis. So I is nothing, it is the moment of inertia. It is the minimum moment of inertia, and minimum moment of inertia will be when we take moment of inertia about the longitudinal axis. So it is the moment of inertia about the longitudinal axis of the body. So, and the shape for which we are finding the moment of inertia will be at the body when it is at the interface of the surface, interface of the fluid surface. Here we will talk about, this is the interface surface area of the body which comes into the picture when we talk about the moment of inertia, when we have to find the moment of inertia. And in that case, this is the okay, so this will be the surface area for which we have to find the moment of inertia. So the moment of inertia is of this body is to find at that section where the body and the free surface of the liquid intersect. Okay, so now moving on, and this is how we have to find when we have to find it. Sometimes question asked in the examination to find the time period of oscillation of the body when we give a small displacement. The body is about to oscillate at a metacentric point. So this is how we have to find. We can find the metacentric. We can find the time period of the oscillation. So kg is nothing. It is the radius of gyration. It is the radiation. It is a minimum. K is the minimum radius of gyration. So we know that as the gm is high, that is the metacentric height is more, the time period will be less. So this is the reason why the cargo ship has less oscillations, because in the cargo ship the metacentric height is very much as compared to some small ship. So that's why it is cargo ship are more stable. They have very less oscillations. Okay, so there are three terms comes into the picture: rolling, pitching and yawing. When the ship, talking in terms of ship, when these are the rotation of a body, in three perpendicular Cartesian axes. So this is a ship, this is direction of motion. When this ship is rotate about the vertical, about the longitudinal axis, this is known as rolling. When it will rotate about the vertical axis, it is known as yawing. And when it will rotate about the transverse axis, this is known as pitching. So rolling is nothing, it is the condition when, say, it is in direction of some ship or some body, when it will try to rotate about the longitudinal axis, this is known as the rolling and pitching. So if we have to find out the moment of inertia of the surface, say I y y, about the I y y in case of rolling and I x x in case of pitching, so that from this we can say the moment of inertia that is I x x is more than I y y. So the moment of inertia case of rolling is less than, so moment of inertia case of rolling is less than moment of inertia in case of pitching. So from this diagram we can say if the moment of inertia is less, the GM will be less. Then GM will be less, the condition will become more severe because it will oscillate very much. I have talked earlier, for the metacentric height to be much higher, it will become more stable. So when in case of rolling, the oscillation is very much severe. severe. So we can say, so that's why we have to design the criteria as per the rolling. If the ship is safe in the rolling condition, then it will surely be safe in case of pitching condition. Okay, so now moving on, so let's just talk about an example. It is a GATE 2016 question. Here the large vessel shown in the figure contains oil and water. This is oil and water, and a body is submerged at the interface of oil and water such that 45% of this volume is in oil and while the rest is in water. Say volume of this body is V. So 45% of this volume is in oil. Here 0.45 V is in oil and 0.55 V is in water. The density of water is density of body. So we have to find the rho of this body. And so there is one thing missing. It is the oil of specific gravity 0.7, and we know that specific gravity of water is 1. So how can we find out? We have to find the separate buoyancy force which is acting by the oil and the water in that body and balance the forces in the vertical direction. So the weight of this body will be acting downward, say mg. So we can write balancing the force in the vertical direction. So force is acting downward of this weight, mg, will be equal to the buoyancy force of this applied on this body due to the oil plus buoyancy force acting on this body due to the water. So we can say Fb water plus Fb oil. And mass, we can write mass is rho into volume of this body into g, and buoyancy force by water will be rho of water into volume of water into g, volume of water displaced. Similarly, rho of oil, volume of oil into g. Cancel out the g in every term. So it will become rho v will equal to density of water is 1000. Volume of water displaced is 0.55 v. 0.55 v plus density of oil is specific gravity is 0.7, so the density will be 100, and volume of oil displaced is 0.45 v. So now cancel out the v from each side, so it will become density 100 into 0.55 plus 700 into 0.45. So it will comes out to be 6865 kg per meter cube. So this is the density of body. So this is how we find out the buoyancy force which is acting on a body when a body is in submerged or in floating condition. So now moving on, this is another example which is asked in GATE 2016. For a floating body, the buoyancy force acts at, I told you earlier, for a floating body, the buoyancy force is always act at the centroid of the displaced volume, of fluid. So here in this options, so it is option D is correct, the centroid of the displaced volume. So option D is correct. No need to check out the other options. Center of the floating body, no, it is not at the center of the floating body. Center of gravity, it will not act on the center of gravity, it will act the centroid of the displaced fluid, so option D is correct. So this is all about the buoyancy in flotation. So in the next topic, in the next video, we will discuss about some previous year GATE questions, and I will be covering the question from the topics that I have covered earlier in the videos. We will cover the fluid properties, fluid properties, surface tension, viscosity, etc. And apart from this, we will be covering some questions from hydrostatic law and also from that portion buoyancy and flotation. Okay, so for this now, thank you.